Right. So in the last class, we looked at this chain rule for derivatives in general for functions from Rn to Rm. And I also gave some geometric interpretation of what the derivative could mean. So this was in terms of the normal to the tangent hyperplane at a given point on the surface that defines the function. Right. So that's one interpretation of the derivative or the gradient. There could be multiple other interpretations, but probably what is also relevant to us in the context of convex optimization is the following. So if you think of the derivative of a function at a given point, right? So you have a function that defines a curve, right? If you take any point, what does it mean? So the derivative can either be positive or negative, right? So if it is positive, what does it mean? What can you say about the function? It's increasing, right? Similarly, if I take the derivative at some other point and it turns out to be negative, it means that it is decreasing, right? So another way of thinking about it is I take a given point. If the derivative is positive, then if I go to the right, the function is increasing. And if it is negative, then it means that if I go to the left, then the function, if I towards the left, the function is increasing. All right. So in some sense, it gives us the direction along which the function is increasing or decreasing. If you just know what the sign of the derivative is. And the magnitude of the derivative would tell you by how much the function is increasing in some sense, in some loose sense. Right. So another interpretation of the gradient of a function is that it tells us along which direction the function is decreasing or increasing the maximum in some sense, right? So for any function and any unit vector or any direction, you can define the so-called directional derivative, right? It's defined as follows. So the directional derivative of a function f at a point x along the direction u is essentially this. It's exactly the derivative of a function that you think along one particular direction, right? So this gives the directional derivative, and this depends both on the point at which it is evaluated and also the direction along which it is evaluated, right? So if you fix a given point, you can look along all possible directions around that point and see along which direction the derivative is maximum or minimum. And this is a homework problem. So find an expression for the directional derivative for a given direction, and it turns out that you can find an expression for the directional derivative in terms of the gradient. And what you can also show is that the directional derivative is the minimum if you look along the direction of the negative gradient. So basically, this is minimum if you take u to be equal to the gradient of f evaluated at x divided by the norm of the gradient of f evaluated at x. This is a homework problem. It's also there in your assignment 1. All right. Any questions? Okay. So just as we define the derivative and the gradient of a given function, we can also define the second derivative. And the second derivative is nothing but the derivative of the derivative. Right? Can one of you turn off this light? Yeah. Great. So as we saw, if I have a function f, let's say from Rn to R, what can you say about the derivative of the function? What would it be? It's a 1 cross n matrix, or you can also think of the derivative as a function from Rn to Rn, right? Because for every vector x, I get another vector. It's a row vector, of course, but for every vector x, I get another vector, df of x. So what can you say about the derivative of the derivative? What should it be? It can be represented as an n by n matrix, right? So that's just it. So that gives you the second derivative of the matrix, and it's essentially the Jacobian of the Jacobian. So you can write it as dou square f by dou x1 square, dou square f by dou x1 x2, x1 xn, and so on. Of course, the second derivative is equal to this matrix only if the second derivative or all the second order partial derivatives exist and are continuous. Okay. But in most examples that we'll see, at least almost everywhere, we'll see that this will always hold. Okay. And the transpose of this second derivative is what we'll call the Hessian. And if the second order partial derivatives are all continuous, then the Hessian turns out to be a symmetric matrix, or the second derivative is also a symmetric matrix. So the second derivative is equal to the Hessian matrix. All right. Can you repeat what it is? Right. So firstly, so throughout we'll assume that all of these second order partial derivatives exist and they're all continuous at x1 through xn. So if that is the case, then firstly the transpose, no matter what happens, the second order, the transpose of this will always be called the Hessian. If this matrix, if all dou square f by dou xi to xj, if these are all continuous, then the second derivative matrix is also going to be symmetric. Okay, which means that the Hessian is equal to the second derivative, because the transpose of this is the Hessian, and this is equal to the transpose itself. Right? Then we get transpose, we get gradient if it is R or into. Correct. And then we do a transpose that says Hessian. Why are we transposing it? For us to take a derivative. It's just a matter of definition. Right? I could have defined everything. For example, here I could have said that the derivative is going to be 1 cross, instead of saying that the derivative is a 1 cross n matrix, I would have said that it's an n by 1 matrix. But the terminology, notation wise, the derivative is always represented as a 1 by n matrix rather than an n by 1 matrix. And that really comes from the definition of the derivative, which is, yeah, the definition over here, where I'm writing this as df of x times y minus x. Instead, if I define this as df transpose times y minus x, then everything would have been, there wouldn't have been this difference between the derivative and the gradient. It's just a matter of notation, nothing else. But the nice thing, since I don't use the transpose, the chain rule becomes much simpler, because then it is just dg times df. Otherwise, I would have some transposes sitting in here. That's the convenience that we get. Okay, any other questions? Correct. So in case all of these are continuous, then it doesn't matter. Correct. So here we'll assume that when I say dou square f by dou x1 dou x2, I take the partial derivative with respect to x2 first and then with respect to x1. But throughout we'll just assume that the second order partial derivatives are all continuous, which means that dou square f by dou xi dou xj is the same as dou square f by dou xj dou xi. Alright. Okay, some very quick examples. So suppose I have f of x is equal to the 2 norm of x the whole square. What would the Hessian matrix look like? So what is df of x? Yeah, it is 2. What should be the dimensions of the derivative? 1 cross n. So it should be 2 x transpose. Right? The gradient would be 2 times x. And what would be the second derivative? I mean, just think about it in terms of this matrix. Yeah, all 2's. So it's going to be an n by n matrix with every entry is equal to 2. Yeah, it's going to be a diagonal matrix with all the diagonal entries equal to 2, or it is nothing but just 2 times the identity matrix. Right? Okay, let's take f of x is equal to some vector b transpose times x plus some real constant c. What is df of x? Yeah, it's going to be b transpose. And what is df square of x? It's going to be the all zeros matrix. Right? So you can evaluate this as an exercise. Let's look at x transpose ax. What would be the second derivative? Okay, it's just going to be a plus a transpose. Right. The first derivative is a plus a transpose times x, and we've seen previously that the derivative of some b times x is simply equal to b, right? So in fact it's going to be b transpose, but this is anyway a plus a transpose is always a symmetric matrix, so the derivative of this is just equal to df square, which is equal to a plus a transpose. Any questions? Yeah, you're right. The derivative would be x transpose times a plus a transpose, and the second derivative is a plus a transpose. You're right. Any other questions? Okay. So with this, we've covered at least some basic real analysis and calculus that we need in this course. So next, I'll quickly go through some basic linear algebra concepts that we'll require, and then we'll get into convex optimization, right? But this is perhaps a good time to have a short quiz, all right? For that, please make sure that there are no more than 3 people in a bench, and keep all written material and mobile phones in your bag or somewhere below. You can keep your bags with you, but make sure that all written material is taken. Did everybody get a sheet? All right, please settle down. Write down your name and roll number at the top, and you just have to write the final answer, nothing else. Just question number, final answer. You can take 5 minutes, so pretty short. Yes. Which one? It is there. Quality. If it's not clearly visible at the back, A is the set of all 3 to the power minus n, where n is an integer. That's fine. You write that. But I can't do your practice. You just have to write the final answer. Right. Find in the sense, yeah. Just one word or one phrase answers. No derivation, no calculation. Is A closed? I just want yes or no. I'm not going to look at the answer. Everything is just has to be a one word or one phrase, and all the information we have. Right? Yeah, one word or one phrase. The last one is f of x equal to x transpose ax. The gradient is equal to what? Can't find the gradient. We'll take one more minute. So you've written your name and phone number. What are the answers? Yeah.
Why not 9?
It has to be the infimum, right? The infimum is the greatest lower bound. So it's 0. Right? Okay. Okay, please settle down. Okay. So let's very quickly go over some basic concepts in linear algebra. Again, most of these, the first part of this you would have already covered in your matrix theory or linear algebra course, but there would be some things here that maybe you've not seen before, or at least not in this particular form. Right. So we'll start with the very basics. Quickly, what is a vector space over R? A vector space is just a non-empty set V with two operations, addition, which takes two vectors and outputs another vector, and a scalar multiplication operation, which takes a real number and a vector and outputs another vector. Right? And these operations have to satisfy a bunch of properties for this to form a vector space. Addition should be commutative, addition should be associative, there should be a special vector in the vector space called the zero vector, such that adding it to any vector gives you the same vector itself. And similarly, for every vector you can find the negative of that particular vector, such that if you add the negative to the vector, then you get the zero vector, right? And so that's about just the addition operation. The multiplication operation should satisfy certain properties. Multiplication should be associative. It doesn't make sense to define commutativity because we always assume that the first, so the multiplication is a map from R cross V to V. So the first element is always a real number and the second element is always a vector. Right. Similarly, you have the addition and multiplication interact with each other through this distributivity property. That is, any scalar times the sum of the two vectors is equal to the scalar multiplied by the first vector plus the scalar multiplied by the second vector. And similarly, sum of two scalars times a vector is equal to the sum of, is equal to product of the scalar times the vector plus the second scalar times the vector. Right? And we also need this additional property that, so over the real numbers you have a special number which is 1. Anything multiplied with 1 gives the number itself, and similarly we want 1 times any vector to be the vector itself. Right? So any set that satisfies, along with these operations addition and multiplication, that satisfy all of these properties forms a vector space. Right? And by definition, if you look at Rn satisfies all of these properties and therefore forms a vector space. All right. Some more definitions. If you have a vector space and you take any subset which forms a vector space in itself, that is, it satisfies all of these properties above, then we call it a subspace, a vector subspace of V. And a fundamental concept in linear algebra is this notion of linear independence. They are given a set of vectors from a vector space. They are linearly independent if you take any non-trivial linear combination of these vectors, then you get a non-zero vector. Or in other words, the only way you can take a linear combination of these vectors and get 0 is only if all of these coefficients are equal to 0, right? So that is what it means to be linearly independent. And so using linear combinations, you can in fact generate a subspace. So you take any subset of vectors from a vector space and take the set of all possible linear combinations of these vectors. This is called the span of those vectors, and it forms a vector subspace. Okay? And any set of vectors or any subset of vectors of a subspace which are linearly independent and span S forms what is called a basis. Right? And although the basis for a given subspace or a vector space may not be unique, the number of such vectors that you can have, the size of the basis is always unique for a given vector space, and that's what we call the dimension. Right? So this I assume you've all seen before, but so let's very quickly go through some simple examples. So for each of these, we want to know whether it forms a vector space or not. If it is a vector space, then what is the dimension and what is the basis for this particular vector space or subspace? So Rn is a vector space. What is the dimension? It's equal to n. And what would be a basis? So the standard basis, where the ith standard basis vector is basically all zeros except a 1 in the ith position. Right? Okay, good. What about the set of all m by n matrices with real entries? Is this a vector space? What is the dimension of this particular vector space? It is m times n. And if you say that the dimension is m into n, then you should produce a basis of exactly this particular size. Can you give me a basis for this particular vector space? Correct. So basically I can say that Aij, let us say that, so for any I comma j, Aij is the matrix which is equal to, so it's a matrix whose I comma jth entry is 1, others are 0. Right? So in the, let's assume that m and n are equal to 2, then A11 would be this matrix, A12 would be this matrix, A21 would be this matrix, and A22 would be this matrix. Right? You can convince yourself that all of these vectors are linearly independent, and indeed you can generate any 2 by 2 matrix using just a linear combination of these matrices. Right? Okay. What about the set of complex numbers? Is the set of complex numbers a vector space? Yes. And what is the dimension of this particular vector space? Yes. So we're only looking at vector spaces over R. So then it's a vector space with dimension equal to 2. Right? Can you give me a basis? 1 and I. So the dimension, again, as I said, we'll only be looking at vector spaces over R. If you're looking at a vector space over the set of complex numbers, then the dimension of this would be equal to 1. but in this case the dimension is equal to 2, right? So a basis would be 1 comma I, right? All right, what about the set of rational numbers or set of all vectors with rational entries? Okay, it's not a vector space. How many say yes, it is a vector space? How many say it is not a vector space? Some of the hands are not up. So, okay, if it's not a vector space, why is it not a vector space? Zero is there, right? Zero is a.
It's not.
It is not closed under scalar multiplication. For example, if I take any vector over here and multiply it by say root 2, then I don't get another vector with rational entries. So closure is important for it to be a vector space. Again, as I said, we're looking at vector spaces over R, right? So in this case, this is not a vector space. Okay, let's look at the set of all n by n real symmetric matrices. Does this form a vector space? Yes, it is a vector space. And what is the dimension of this particular vector space? It's n into n plus 1 by 2. So if you take, let's say, a set of all 2 by 2 symmetric matrices, you can look at the following basis. Right? The dimension in general is going to be equal to n into n plus 1 by 2. Essentially, you fix all of the entries. Once you fix the entries along the diagonal and above the diagonal, everything else gets fixed. So the number of basis vectors that you have, the number of degrees of freedom that you have, is only in the entries which are along or above the diagonal, and the number of such entries is just 1 plus 2 plus 3 plus 4 and so on up to n, which is just n into n plus 1 by 2. All right. Okay. What about the set of all polynomials with real coefficients and having degree less than or equal to n? It is a vector space, and so what is the base? What is the dimension of this particular vector space? It is n plus 1. The dimension is n plus 1, and can you give me a basis for this? 1 x square, essentially all possible monomials, right? What about the set of all polynomials of degree exactly equal to n? Okay, some of you say that it is not a vector space, and why is it not a vector space? Addition.
Which is not equal.
Why is that a problem?
So then the basis does not span as the coefficient of the last.
Which basis? I'm not asking if this is the basis for that set, right?
X plus x minus x and x plus 1, which is not exactly a
Even more fundamental reason,
Not
the zero vector does not exist, right? The zero vector would mean the zero polynomial, and for that the zero polynomial has degree equal to 0, which is not n. What about the set of all possible polynomials of all degrees? Is this a vector space? It is a vector space. What is the dimension of this vector space? It's an infinite dimensional vector space. And the basis for this would be all of the monomials, 1 x, x square, x cube, and so on. So it has a it's a countable basis, a countably infinite basis. Okay, good. So again, a quick whirlwind of what, suppose I give you an M by N matrix A. What are the four fundamental subspaces associated with this particular matrix? So first, it's the column space, which is the span of the columns of the matrix. That's a vector subspace of Rm, right? The row space, which is the span of the rows of A, which is the vector subspace of Rn. The right null space, so it is the set of all vectors y such that A times y is equal to the 0 vector, which is a vector subspace of Rn, and the left null space, which is the set of all x such that x transpose A is the 0 vector, which is a vector subspace of Rm. Right? Or in other words, you can think of the left null space as the right null space of A transpose. Okay, and what is the relationship between, okay, so firstly, given a particular vector space, as I said, you can look at the span. Each of these is a vector space in itself. It's a vector subspace of the appropriate ambient space Rm or Rn. What is the dimension of the column space equal to? The rank. So this is equal to the rank. What is the dimension of the row space? The dimension of the row space is also equal to the rank. The dimension of the right null space is called the nullity, right? And similarly, you can also define the dimension of the left null space. And what is the relationship between the rank and the nullity? Right, so rank of A plus the nullity of A, this should be equal to the number of columns, which is n, right? Similarly, the rank of A plus the dimension of the left null space of A, which is the nullity of A transpose, should be equal to m. Right? Okay, great. A very quick exercise. Again, you can do this almost by inspection. Compute all of the four fundamental subspaces of this particular matrix. So just by inspection, what is the rank of this matrix? Equal to 1, because you see that the second row is essentially just a multiple of the first row. Similarly for the columns. So can you give, when I say compute the four fundamental subspaces, when you have to compute a subspace, essentially you have to compute a basis for that particular vector space. So let's compute maybe the row space. Yeah. You can just take 1, 3. Right. So any alpha times 1, 3. This is basically equal to the row space. Right. What about the column space? You can take any column, either 1, 2 or 3, 6. So alpha times 1, 2. This gives the column space. What about the right null space? Can you give me a basis vector for P1? You can take one basis vector is 3 comma minus 1 or minus 3 comma 1. So alpha times this for all alpha in R. This is equal to the right null space. You can take 2 comma minus 1. Okay, good. So now we are all comfortable with these subspaces, right? Great. And you've also seen, given a matrix, how do you find the row reduced echelon form, or how do you do Gaussian elimination to solve a system of linear equations, right? So essentially it's a combination of a sequence of operations on, or row operations on the matrix. And there are three fundamental types of row operations. One is you take a row and subtract some scalar multiple of another row to get the new row, right? That's what I'll call a type 1 operation. You take Ri, you take the ith row, you subtract the some alpha times the jth row from it, and then you replace the ith row with this particular quantity, right? That's one operation. Second type of operation is rescaling. So you take the row and you multiply all of the elements of that row with some scalar multiple of itself, some alpha times the same row. And the third kind of operation is you just exchange two rows. So those are the fundamental row operations, three types of row operations, right? And the main property is that any sort of elementary row operations on the augmented matrix, so if you have a system of linear equations Ax equal to b, and you form this where, let's say, this is an m by n matrix A and B is an m length vector, then this m by n plus 1 matrix AB, the augmented matrix, any sort of elementary row operations on these do not change the solution space. So you use Gaussian elimination to bring it to sort of, you try to reduce A to an identity matrix or something similar, a diagonal matrix, and then try to solve this particular system of linear equations, right? So firstly, what is the complexity of finding the row reduced echelon form? So effectively, Gaussian elimination boils down to taking the augmented matrix and finding the row reduced echelon form, right? So what would be the how many operations? Firstly, how many row operations would be required in order to find the row reduced echelon form? So the number of row operations, again a little bit of terminology. When I say row reduced echelon form, I will assume that the matrix finally becomes a diagonal matrix, right? It's not just upper triangular. Okay. So how many row operations do I have to do? Yeah. Okay, why do I need to make n into n minus 1 by 2 operate? Okay. Okay. I'm asking how many row operations are required. Correct. Go on. Correct. So the first, if you take the first column, you want to make sure that all of the first column elements except the first one are all equal to 0. So that would require, let's say, n minus 1 row operations. And then for the second column, you need n minus 2 operations. Third column, you need n minus 3 and so on. in between you may need to do some row exchanges, right? Potentially column exchanges. So roughly the number of row operations would be some constant times n square, right? Or say n square. And how many arithmetic operations are required? I'm sorry, question. Yeah, so it would be order of operations would be order n cube. Yeah.
Can it be from the given notation or the size column number of columns?
Which one? You're right. So this should really be order m square, right? And the number of, so okay, so I'm making a slight simplification over here. I'm assuming that it's the number of rows is proportional to the number of columns, in which case order m square is the same as order n square. So in that case, the number of row operations and the number of row operations would still be order n square, and the number of arithmetic operations would be order n cube. I'm sorry? n cube, how many arithmetic operations are required to do one row operation? So I mean, take one row operation. So you agree that the number of row operations is order n square. Correct. That's okay. I'm not interested whether it's n or n minus 1. That's not a terrible concern for me. Correct. Yes, that's it. Okay. That's good. So now, using row operations, how would you compute the inverse of a particular matrix? Yep, you take A, I, let's call this A double prime. Yep, so what you do is you take this augmented matrix and you perform row operations on this, and you try to reduce it to the form I, of course. So here we're assuming that A is an invertible n by n matrix. Otherwise, there's no point in trying to find A inverse. So you take the augmented matrix A, I, and then you perform row operations to bring it to the form I and some other matrix A prime. Then A prime would simply be equal to A inverse. Right. And hence, what is the computational complexity of finding the inverse of a matrix? Yeah, so number of row operations required would be order n square. The number of arithmetic operations required would just be order n cube. So that's one efficient, computationally efficient way of finding the inverse of a matrix. Have you all seen this before? Hopefully, yes. Great. Again, switching to a slightly different topic. So someone gives you a vector space, right? Maybe the column space or the row space of a particular matrix. Now, using this, of course, you can try to find a basis maybe using row operations or something else. But in many cases, what we want to find is not just any basis for a vector space, but rather an orthonormal basis. So in other words, we want a set of vectors, a basis, such that every vector has unit norm and they're all orthogonal, pairwise orthogonal to each other. And one approach to finding such an orthonormal basis, a canonical orthonormal basis, is Gram-Schmidt orthogonalization. Right? So what do? So you take a set of, suppose that somebody gives you a set of vectors x1 through xn. For now, let's assume that these are all linearly independent. If not, you take a subset of vectors which are actually linearly independent, and you perform the following sequence of operations. You first define, let's say x, you take x1 and you normalize it. So that's your first vector in your orthonormal basis. And then you form x2, let me call this y1. So next I form x2, which is I take x2 and I subtract the component which is along x1. So the component along x1 would just be the inner product between x1, or let me say the component along y1 x2 times y1. Right? So effectively what I'm doing is I took the first vector, this was my y1, and I have some other vector, let's say x2, which is not orthogonal to y1 and it's neither is it of unit norm. So basically I find the projection of x2 along y1 and subtract the projection. I can decompose x2 along y1 and orthogonal to y1. That gives me some vector, and then I normalize it. Let me call this x2 prime. So y2 is simply x2 prime divided by the norm of x2. Right? Now I have two vectors, y1 and say y2, which are orthogonal to each other. I take x3. Right? Now this x3 could be some other vector which can make an arbitrary angle to y1 and y2. I again decompose it into two, one which is along the subspace that is spanned by y1 and y2, and another which is orthogonal to the subspace spanned by y1 and y2. Right? So that gives me x3 or x3 prime. This is x3 minus the component along y1 minus the component along y2. And then I just normalize what remains. Right, and I keep repeating this. So this procedure, as long as I start with a basis or a set of linearly independent vectors, this is guaranteed to give me an orthonormal basis to the span of those vectors. All right. But the one thing to note is that the orthonormal basis that I eventually get would depend on what order I took these vectors. If I chose these vectors in a different order, if I just shuffled them, then I'd get a different orthonormal basis for the same span. Right? Any questions? Yeah. You can, right? Yeah. Is that a question as to whether you can interchange or not? So again, I'm assuming real vectors throughout. That's why I can effectively interchange the inner product between two. So throughout, everything is in terms of the reals. So in this case, the inner product is a symmetric operation. Question?
So you divided everything by the normal. If you did not do that,
I'm sorry, this should be x1 prime, x2 prime. Yeah.
if you did not do that,
Yeah.
at the end, you will get an orthogonal. So there,
No, if I didn't divide by the norm, then firstly, I should also be dividing these inner products by the norm. Okay, so you have to be careful with that. That's number one. And in the end, if not, then towards the end, I would get an orthogonal basis, not an orthonormal basis. Each of the vectors? Yes. They would all be scaled versions of this orthonormal basis, nothing else. Questions? Any other questions? Okay.
Scaled but not uniformly scaled, right?
Yeah. They all have different norms.
That's not.
Yeah. They would all have different norms, for sure. Right? Okay. Now let's see the definition of a determinant. I'm not sure, you may or may not have seen this particular definition of a determinant. All right. And I'm going to define the determinant of a matrix in terms of permutations. Right. So what is a permutation? A permutation is just a bijection from the set 1, 2, 3 to n to itself. Right. So for example, 1, 4, 2, 3 is a bijection of 1, 2, 3, 4. So basically 1, 2, 3, 4. I can write the permutation as 1, 4, 2, 3 because it is like I map 1 is mapped to 1, 2 is mapped to 4, 3 is mapped to 2, and 4 is mapped to 3. Right? So that is what I mean by the permutation. So sigma of 1, in this case, sigma of 1 is 1, sigma of 2 is 4, sigma of 3 is equal to 2, and sigma of 3 is equal to, sigma of 4 is equal to 3. It is a sequence, but it's not any sequence. It's so all of these entries are going to be different, and they're just going to be 1, 2. It's just a shuffled version of 1, 2, 3 up to n. And it's a fixed length sequence. It's not an infinite sequence. All right. You just take 1, 2, 3 up to n, and then shuffle all of these elements. You get a permutation. Nothing else. Okay. But a nice feature about permutations is the following. So suppose I take any arbitrary permutation. Let's take 1, 4, 2, 3. Right. So I can start with 1, 2, 3, 4 and try to perform a sequence of pairwise swaps. So what is a pairwise swap? I take two elements and I just interchange those two. For example, I take 1, 2, 3, 4. I exchange 2 and 4. Right? I exchange these two. I'll get 1, 4, 3, 2. Right? let me perform another pairwise swap. Let me exchange 3 and 2, and I get 1, 4, 2, 3. Okay. Now it's obvious that given any permutation, I can reach this particular permutation from 1, 2, 3, 4 using a sequence of pairwise swaps, right? And the number of pairwise swaps that I need to make need not be unique, and it need not be the same set of swaps. For example, to get 1, 4, 2, 3, I could start with 1, 2, 3, 4. I could first exchange 3 and 4, perform one swap to get 1, 2, 4, 3, and then exchange 2 and 4 to get 1, 4, 2, 3. So in both these cases, I had to do two sets of swaps, two pairwise swaps, but different swaps, right? Two different ways of reaching 1, 4, 2, 3 from 1, 2, 3. Again, remember, I'm only allowed to make pairwise switches, nothing else. But then you can see that to go from one to the other, it need not be just using two swaps. I could, for instance, take 1, 2, 3, 4, swap 1 and 2 to get 2, 1, 3, 4. So I have 1, 2, 3, 4. I could make some unnecessary swaps, 2, 1, 3, 4. Again, swap to get 1, 2, 3, 4. And then swap to get, let's say, 1, 4, 3, 2. And then make another swap to get 1, 4, 2, 3. So in this case, I could do this using two swaps. In this case, I need 4 swaps, right? So the number of pairwise swaps required is not unique. That's one thing to keep in mind. Let's take another example. Let's just take a simple permutation, 1, 3, 2, 4. How many swaps do I need to go from 1, 2, 3, 4 to 1, 3, 2, 4? Just one swap is enough, right? I just exchange 2 and 3 and I can get 1, 3, 2, 4. Is there a way of getting going from 1, 2, 3, 4 to 1, 3, 2, 4 using two swaps? Two swaps. Two pairwise swaps. The answer is no. Right? In fact, if you want to go from 1, 2, 3, 4 to 1, 3, 2, 4, you will always require odd number of swaps. It's always going to be odd. Similarly, if you want to get to 1, 4, 2, 3, the number of swaps that you require will always be even, right? And so for any given permutation, the number of swaps that you require to go from 1, 2, 3 up to n to that particular permutation, it's always going to be odd or it's always going to be even, right? And for a given permutation, we'll say that the sign of this permutation is +1 if the number of swaps required is even, and it will be -1 if the number of swaps required is odd. Okay?
You're taking 5 to 3 plus 2n and the weights.
Yeah, we always start from 1, 2, 3 up to n, and then find the number of pairwise swaps that are required to get to this particular permutation. Okay? Using this, we can define the determinant infinite. You can make any number of trivial swaps, right? That could change. That could depend on the permutation that is given to you. Correct.
There's a minimum number in terms of
That depends on what sigma is, right? So in this case, I could do it using one swap. In this case, I could do it using two swaps, but that really depends on what permutation you begin with. Yes.
Minimum number of surfaces.
Oh, how many would be, what is the minimum that, in the worst case, what is the minimum number of swaps? I think n minus 1 probably would be the worst. Maybe, I'm not sure. But anyway, we don't need that particularly. We don't care what is the minimum number of swaps required to go from 1, 2, 3 up to n to that particular permutation. We just need to know whether it's even or odd. All right. So using this, we can define the determinant as follows. So it's just summation over all permutations sigma of, so if I have, if Aij is the ijth entry of the matrix A, then it is A1 sigma of 1 times A2 sigma of 2 up to An sigma n times minus 1 or times the sign of sigma. Okay, so this is how I'm going to define the determinant, right? So you sum over all possible permutations of 1, 2, 3 up to n. You multiply the 1 comma sigma of 1th entry with the 2 comma sigma of 2 entry, 3 sigma of 3 entry, and so on, right? Times the sign of this particular permutation.
Whatever it says, the multiplication will always be.
No, so let's see some specific examples. All right, let's take a simple 2 by 2 matrix. So you have 1 comma 2. How many possible permutations can you make out of 1, 2? Two different permutation. One is the identity permutation. 1 comma 2 gets mapped to 1 comma 2. The other is this particular permutation, right? What is the sign of this permutation? 0. So this is plus 1. And this is minus 1, right? So in this case, sigma of 1 is 1 and sigma of 2 is 2. And in this case, sigma of 1 is 2 and sigma of 2 is equal to 1, correct? Now let's use this particular formula. Okay, so what do I have? The first term should be, let's take this particular sigma, right? So 1 comma 2 is one permutation and 2 comma 1 is the other permutation. So I take A 1 comma sigma of 1. What is sigma of 1? 1 itself, times A2 sigma of 2, which is A2 2, times what is the sign of this permutation? Plus 1. And let's look at this permutation, A1 comma sigma of 1, which is 2, times A2 comma sigma of 2, which is 1, times the sign of this permutation, which is minus 1. What happens when you add the two? You get A11, A22 minus A12, A21, which is the formula for the determinant that you've seen in high school. Okay. We can try to do the same for a 3 by 3 matrix, right? So in this case, you have 1, 2, 3. How many permutations do I have? have 6 permutations. So you can list down all possible permutations of 1, 2, 3. Find each of these, the sigma, what is the sign of each of these permutations, and try to use the formula to evaluate the determinant. You'll see that you'll end up with the same formula for the determinant that you've seen in high school. Right? So this is a very generic definition of the determinant. Okay, so I leave it as a homework. Find this. All right.
You chose 1, 2 for the top row and 2, 1 for the bottom. Or can it be like extension?
Which one?
The
So
1, 2 and 2, 1.
I didn't quite follow 1, 2, 2. It doesn't matter in which, whether you take this first or this first, right? Because I'll just get A12, A21 times minus 1 plus A11, A22. That's it. Nothing changes. Right? So if I use this formula to find the determinant, effectively, this is one way of representing. This is a closed form expression for the determinant. You would have also seen an expression for the determinant in terms of minors and cofactors, right? And that is what this will reduce to. It will just be, you can sort of write this in a recursive form to get the same expression in terms of minors and cofactors. But this is something that you can just feed into a program and compute. It's a brute force approach, right? What is the computational complexity of finding a determinant using this approach? You'd require, there are n factorial permutations, and for each permutation I have to perform order n multiplications. So the computational complexity is n factorial times n, which is huge. It's not feasible to really find the determinant using this particular approach. But this expression is still helpful because in certain cases you have a closed form expression for the determinant, and you can say something about the behavior for, let's say, a matrix valued function. Right? Okay, so let's stop here. So have you seen this particular form of the determinant before? How many of you have seen this before? Okay, maybe a few of you. What other form of the determinant have you seen before? Have you seen anything other than minors and cofactors?
These things, diagonal, then minus this diagonal. I can't remember it is
Okay, so
trace method.
is that the only way you know how to compute the determinant of a matrix?
Except for
Other than the cofactor approach?
the trace.
Okay, there's one which is you find all of the eigenvalues and multiply, but that requires you to find the eigenvalues in the first place. Okay, fine. So we'll see another approach, another way to computationally efficiently find the determinant in the next class. Right?